Hello, everyone, and welcome to today's Cardano Foundation seminar. Today with us, we have Skylar, who is from the VyFinance team. Skylar is with us to present their solution of the implementation of 8 PLC and how this is basically shaping the whole development process for smart contracts on Cardano. Now, Skylar will be taking questions between the session. So if you have any questions, please feel free to raise your hand or submit your questions into the chat. If you feel uncomfortable for whatever reason, you can always use the anonymous Q&A session, which is on the bottom right corner at the box. You can click that and there's a Q&A. Without further ado, Skylar, I'm handing it over to you. Thank you.
Thank you for that introduction, Denisio. Yeah, I'm from VyFinance. I've been working on building out the V3 DEX, our biggest product so far. And we kind of went a different route for creating our DEX. We felt that the tooling that existed wasn't necessarily sufficient for what we needed, and there was a lot of questions that we had along the way. And so we ended up kind of carving out a new path toward dApp development in the ecosystem. And so essentially we've been able to go from Jai right to UPLC, and I'll talk a bit about why that is a novel approach and what kind of benefits we get. So let's see here. So the first thing I want to start with and kind of is like the story of how we got here. So developing for Cardano is hard. I've been in the space for a long time, quite a few years now, and things are still kind of in a difficult place. And we see that all the time. We see common questions, things about Plutus, things about Nix and Haskell. And, you know, as a relative expert on those things, I can still tell you it's a very difficult process, even for people who are experienced. The things that become time consuming, Nix builds, Cabal builds, trying to do package resolution, you know, running nodes. A lot of the things I'm going to mention actually fall into a lot of these categories, right? So Nix is both very complex and very time consuming. And there's like an enjoyability aspect there of it's not as entertaining, it's not as fun. And the reason that matters is that it keeps you in a good headspace and it keeps everything moving forward. There's a lot of issues we had, at least in the past. I don't know how much this has been resolved now, but getting things to resolve, getting a bunch of libraries together to say use Plutus TX to build our smart contracts out and have those the Plutus V3 features enabled. Getting those packages to resolve together and getting Cabal to be happy and Nix to be happy was a very difficult process and was starting us down the road of wanting to kind of see if there was a better way. We took a look at Icon, which I will talk about, you know, probably a little bit later, but there were some things there that weren't as agreeable as we'd like to. So why is development on Cardano difficult? Why is it hard, right? Especially compared to potentially other chains. Now, I think the design of the chain and like the consensus mechanism, the smart contract mechanism, I think it's all very good. It's just there's this absence of discoverability, right? Even finding out, let's say, as a test, you can test this as like, what is actually included in Plutus V3 from a technical perspective, things that a developer would care about, what built-ins become available, you know, that sort of thing. Like where would you even find that information, right? Things about, you know, transaction building, what constitutes transaction. You can look at the, you know, CDDL and you can go from there, but a lot of people don't even know where to find those things. And so there's this absence of discoverability where technically the information is all there, but it's very difficult to find a unified place or unified spec, right? We end up what I say is building on folklore, meaning you know, something like wallet unfracking. We kind of hear these things from different builders in the community and we propagate them and we're doing them, but a lot of it is folklore and that it's not real, it's not tested, right? Like we discovered fire before we discovered thermodynamics, but at this stage we should be looking for, you know, the manual on thermodynamics, right? When we're building on the chain. And so we spend a lot more time actually looking for information than we do building things. Or we build things on folklore and then we don't get like the best bang for our buck, the best performance or the best feature set that we could, right? And so that discoverability gap leads to what I call like a depth first search versus a breadth first search problem. A big thing that we also wanted to do when carrying out this process was to make that more of a breadth first search problem. And what I mean by that is if I want to build something, I end up having to delve into tons and tons of details before I can move forward, instead of only really trying to target the information I need at the moment. That slows down development. I'm looking through SIPs, I'm looking through talks, I'm looking through white papers, I'm looking through the implementation itself. There's plenty of times where I'm looking at Cardano node source code or reading through the NICs or trying to reverse engineer things. And so accidental complexity kind of becomes the bane here. Lots of tools are created out of misunderstanding or features that aren't used. We've had like large, long debates about transaction building, collateral, internally and with other teams and other dApps, and even, you know, the Cardano Foundation. And this means a lot of projects, a lot of builders have some of the information correct, but not all of it. And so no one's really using the tech to the fullest. This is also dragging down adoption, because if you're looking to get into it, you like people trying to move in from other chains. There's so much to look at. There's the UTXO model, which already gets people kind of confused, even though it's, you know, it's not too bad, but we could do a better job at explaining it. But then when you're looking at building smart contracts, you have to do a lot, like even finding good docs, finding good library support, all of those things. Like we don't even have, you know, for developers moving in, we don't even have like really great VS Code extensions or anything. Not that I use them, but I could see why they would be super, super duper valuable. And so like 99% of the Plutus smart contracts on chain aren't even being moved to V3. And a lot of people don't even know that there's like a signature change internally in the UPLC that constitutes V3. Like there's just so much missing information. So essentially we get these layers of sediment that prevent people from like holistically utilizing all of the features in the chain and moving quick and building cool stuff. And then also from that, there's a practical problem of the contracts produced with that sediment are going to have high fees or transaction building issues, and it's not going to be super obvious in the moment what to do to solve those issues because of that depth first search issue. You have to kind of go and become a domain expert entirely before you can start to do these things, without relying on huge libraries as middlemen and hoping that they don't break during a hard fork. And so what we try to do is kind of this experimental archaeology, where I wanted to step away from the kind of information that's there and kind of test it against some direct source of truth. In this case, it was the chain. So it's like, can we just produce UPLC directly? And can I just give that to the chain, give that to a node, submit that on pre-prod or mainnet, and see what happens, and the kind of learn the information from there, try and box out this information from trying to get this information out of a black box, right? There's drawbacks to this approach, which is that there's going to be a lot of tried and true kind of domain knowledge that we miss or we have to rediscover. But the point of doing it this way was to always be able to move forward, right? We're not dealing with CHaP, we're not dealing with NICs, we're not dealing with obscure build errors, we're not dealing with like weird integration of libraries and issues and things like that we had to. And as like a marker, when we tried to do Plutus V3 before in Plutus TX, we had to, I hand patched maybe 40 different libraries to get them all play nice together, because even though CHaP, all the versions they were all released about the same time, across all the repos, there's still been some dependencies that didn't really work. And because Nix was pinning all of those dependencies, you would run into small little errors, like a type in this library changed slightly, and now these packages are broken, et cetera, et cetera. So again, I don't know if that is the case still, but I know a lot of people have kind of echoed the sentiment of like, yes, I don't like having to work with these things. It's all very difficult, and I don't really understand where to go from there. Yeah. So that's kind of what I would expect. And again, it's like, I get that it's hard. It's like there's so many packages, so many teams. There's a lot of bureaucracy around it. But I wanted to kind of cut through all of that and just be able to have a really solid developer experience for us while making our decks and pushing the limit of what you can do on Cardano. But also to be able to kind of collect that information and contribute to that lack of being able to find information, that divide that we're missing. And so what we needed in our DEX was, I guess let me back up a sec. What I wanted to have was at least the possibility to utilize all of the features of the chain, because a lot of the kind of architectural exploration phase of building that DEX is like, we could just do what is like the tried and true thing. We could go look at all the other DEX smart contracts. We could look at our original smart contract and we could just say, let's just like do this, but V3. But then what would be the point, right? We want to push the limit. We want to like make people want to move to Cardano. We want people to use our product and be like, wow, this is like really great. And we also wanted to cut down on the fee, right? Because that's like a big deal, especially for a DEX, is like, what is it costing you per transaction, right? And it turns out that that's all just directly related to the smart contract, right? Of course, there's the fee from the transaction itself, but a lot of what you're going to be paying for is like the execution cost on chain, the size of datums, things like that. So it's like, I wanted to have access to all of these different tools just in case the architecture showed me that that would be useful, right? Like, can we make sure we're using reference scripts? Can we make sure we're using, inline datums or reference inputs or those things? And then also, are there built-ins in Plutus V3 that make this type of work more efficient or make it so that we can put more on chain? In fact, ideally, we'd want to move toward complete decentralization for our new DEX, right? Like that was kind of what we were imagining. And so I didn't want to be limited by what existed. And so we decided to just build what we needed. And I've been working with a language called Jai for about, I want to say like 3 or 4 years at this point. And it's this really incredible language, and it does a lot of things right. So for the people who have actually tried to build stuff on Cardano or whatever, like a Nix build of even compiling Cardano node or running or syncing Cardano node, like if you're trying to build some program using, Nix and Haskell, whatever, it can be anywhere from like minutes to hours to do a build, right? And even when we're using, not even to do a build, just to get into the developer shell, just to get into like a Nix shell and then like run something or have a REPL where it's like fast and kind of hot reloading, it's very time consuming. And even the hot reload is not that fast. This kind of compiler, like the Jai compiler, whatever, we can do about 2 million lines in less than a second of like an actual full build. No weird intermediate representation, no features turned off, whatever. Like this is just actually compiling right to what we need to ship, right? And I was like, okay, well, this gives me a whole bunch of stuff. It gives me big introspection into my program. I can analyze the entire AST in code in user space. I can meta program better than it's essentially, imagine a sane version of list macros that are just like type check and real, nothing even close to, template Haskell or anything like that. Like we get a whole bunch from this. And I was like, I bet it would be really easy to extend this to just produce Plutus, to just like go ahead and go right from Jai to Plutus. And that would be like simple, imperative, it'd be a really nice way to build smart contracts without any of the accidental complexity. We don't have to pull in a bunch of libraries. We don't have to pull in all of like Nix and Haskell and all of the CHaP libraries, whatever. We can just like make what we need, right? And so I started working on that. And actually the prototype I was able to do on the plane ride home back from Rare Evo. And it was just very simple and easy to get something up and running that did Jai to Plutus. We ended up needing this, intermediate representation, APLC. And that's just to make UPLC look kind of more Haskell-like. And this is more of an implementation detail. So I know you guys might have been told something about APLC. We're kind of just working on a name for this whole suite of tooling because it evolved to be more than just this, than just compiling to UPLC, but a whole kind of framework to make dApps. And we are going to, you won't be kind of locked into using Jai if this becomes more of a public and adopted thing, which is kind of what we're advocating for. There will be different front ends kind of available so you can write the smart contracts however you want, but you'll still get like the strong typing and strong guarantees that come with the whole package. And so APLC became our intermediate representation because the agreed upon syntax for UPLC with like explicit applies and things like that are just, you don't want to have to think like that. It's a lot of noise. There's a lot of, you were going to write, UPLC by hand, it would be very tedious and annoying. And so APLC just is like more sane. It looks more Haskell-like, and I'll show you guys an example of that. But it looks more Haskell-like. It has support for like actual definitions and names and declarations, things like that. And so APLC was kind of my mental space to be able to work on how certain imperative code becomes like functional. But ironically, yes, exactly. I want to say your name right. It's is it like Michelle or Michael, or I'm sorry if I get it wrong. Based on how it's written, I can't really tell. Okay, Michael's fine. Okay.
Yeah.
And essentially, imperative programs are just easily understood by like most people, even people who don't write software. It's like if you give someone a list of steps, like first you do this, then you do this, then you do this, right? When you do that, it's like very, very obvious, and it's very, very nice for people. And functional programming, as much as I love it, and I love like the mathematical simplicity and of like lambda calculus and things like that, it is a lot to grasp. Like you do need to go and delve into a whole bunch of stuff, especially if we're looking at higher order functions and types or whatever. But I also found this really weird thing while working on doing all of this work for the DEX and all of this work on the tooling, is that functional programming actually maps horribly to Plutus, even though Plutus is a lambda calculus based language, because Plutus is an extremely strict language. And it's so strict, in fact, that it's stricter than C or assembly. Because in like an assembly language, if you were to do like an or, right, like this or this, it will only evaluate the second branch if the first one was false, right? In Plutus, it will evaluate both. If you do an or in Plutus, you are getting both trees evaluated every single time. In fact, everything's getting evaluated every single time. And we have this thing, these rules that we learned, which is that recursion, funny enough, in Plutus is actually bad. Any smart contract on chain that uses recursion is way more expensive and way more costly in CPU and memory. And the reason is because of how the node evaluates a Plutus program. It evaluates the structure using like a sec machine, which is, I mean, that's the technical detail, but essentially it's like how it's run on chain. The cost of using recursion, or specifically like the Y Combinator, it pretty much blows the complexity out of the water for your smart contract. So immediately you're looking at a fee that is like 0.3 ADA just from using the Y Combinator one time. It's very, very expensive. And we found that actually what was good is harkening back to a more imperative paradigm of loop unrolling. And so loop unrolling is essentially, I can give an example here. Let me switch my screen. So if we look at this here, this is going to be an example of APLC. And this is APLC that was produced by the compiler, so it's not really formatted. But for those who are familiar with like, you know, lambda calculus or Haskell, whatever, we have the slash representing the start of a lambda, and then we have the name of something, some variable, and then we have the arrow, and then we have the body of the lambda. And what we're going to do instead of doing recursion is we're going to just apply this function f to itself many, many, many times. And this f is going to just be the body of the function. So instead of recursing in the traditional sense, we are essentially just creating a chain of application that is static. There's a fixed amount. So we unroll to a fixed amount. And what we found is you can actually set this unroll amount very high. In this case, I believe it's set to about 128, which is, you know, for most inputs, for most transactions, for most things you're going to do, orders on a DEX, whatever, you're never going to approach 128 before other limitations in the chain get in your way, like maximum transaction size, max output size, those sorts of things. And by doing this unroll, you create a fixed structure for the sec machine that actually results in way less execution costs. Because the issue with the Y Combinator is it recursively expands to itself, and the sec machine has to traverse that structure a lot to get to actually running your validator. And so just this alone made it so much cheaper to produce contracts on chain that are really, really low in fee. And I'll be doing a comparison versus some other smart contract examples, but just that sort of thing. So, okay, so it's kind of like that, but it's a fixed version of it. So with the regular tail call that you're going to be doing, there's still going to be some recursive element. You're not really bounding the recursion because you wouldn't know that from like the compiler standpoint, right? So if you're compiling like either way, if you're using, so if you use a higher order function, or if you use recursion via like a Y Combinator, you are making the sec machine do a lot of structural evaluation of your program, and you're paying for that in the CPU and memory cost. This unrolling is essentially tail call optimization, but at the same time, the fixed nature of this tail call and the fact that it's explicitly put in means that the sec machine doesn't spend CPU and execution or CPU and memory actually discovering the structure of your program, and it just spends the time discovering it once and then executing it. So let me see what you're saying here. Yes, but at the same time, like with the strict nature of UPLC specifically, this like you can't really do tail call optimization in the same way. Like even if you're using delay or lateness or whatever, you're introducing more structure. It ends up being more cost on chain, and we can go more into like the specifics of that. But yeah, like I'd love to talk to you more about that, Arno. But yeah, essentially that is the difference that we found. So using the Y Combinator versus not using the Y Combinator, the cost is way more. And then if you are using any sort of higher order function, you're doing the same thing. Essentially, when the sec machine evaluates applying the higher order function to the actual body that's using it, it causes essentially a recomputation of the structure, right? So you're not using like the you're not getting the benefit for free. You are essentially having to reapply any place you use that higher order function. Like anytime, like let's say you're searching through a list and you're filtering and you're applying different filter functions, you're paying the cost of applying that function and the structure all the way through, and it ends up being a lot more expensive on chain. So let me go back here, this window here. There we go. And so yeah, so we have some principles here that kind of move into, also the last thing I didn't mention was we're not using force or delay. Not using force and delay, we're not like, you can't really thunk in UPLC because of the way it's strict. It is just not using force and delay allows the execution to be more predictable, and it also simplifies things, especially in the compiler toolchain. So that's something that we're also doing. So some principles that we want to see in the community as far as it goes for tooling is something I picked up from Mike Acton when he was talking about data-oriented design. Mike Acton makes a lot of game engines he used to make them for Insomniac. Now he's kind of helping Unity figure out their mess. But you know, if you played like the recent Spider-Man games, Mike Acton's team was responsible for creating the engine for that. And he really cares about performance and getting things to actually look and feel the way that they should, given the budget, given the hardware requirements. And he had this kind of these peaks of these like brilliant kind of things in that talk where he talks about how there are bad defaults and they lead to bad culture. And bad defaults could be like the standard library in a programming language, right? If that's bad, people are going to import it by default. And yeah. So Matthias, am I saying that correctly? So we don't use force or delay in branching because we can get away with the kind of the weak head normal form type. So if we have an if or a choose data, what we're doing is it's actually just wrapped in a lambda. And by wrapping it in a lambda, we're getting that kind of free, not evaluating it until the lambda gets hit. And so we're not paying for that structure. And then we don't need to actually put an explicit force or delay. So we do omit some forces, but that's just because the spec like mandates that for if then else the built-in because of like typing. Some of them have typing issues. And even though it's untyped Plutus core, you have to apply a force to something to like get it to fake the type argument. But that's not like a true force. That's just kind of like a language detail. And so, yeah, we're not using force and delay in the traditional sense. We create no thunks, we assume strict evaluation, and then things work. Yeah, exactly. We're just getting the laziness through the lambdas in the places where we have to. So if we had like an if with an error on one side, we obviously have to wrap that, right? And if we don't wrap that, then it's just going to error because it's so strict, right? So yeah, so that's what we're doing there. And so we have these bad defaults and they lead to bad culture. And I would say that, you know, the state of like CHaP, for example, is an example of a bad default. I think that it leads people to have to do a whole lot of extra work, and it leads people to produce things that are less than ideal because it's not as fun, it's not engaging. The time it takes to build something makes you drain on your drain on your resources, and you know, you just get like less on chain than you would like, or less from your feature set than you would like. And so we want to kind of focus on performance too, as well as versus the generality. So I think a lot of these tools are created for like the broad spectrum of users. And when you have a more performance-oriented mindset, you're kind of cutting all of the accidental complexity away and focusing on like, what is the actual problem I'm solving here? And that kind of leads to what we did to build our deck. So by building all this stuff out, we're just building it for us. We just wanted to be like, what can we do to have these features for our decks? And we weren't trying to fix the ecosystem. We were being specific, but that leads to why we're here today, which is the fact that by doing this very specific work, we found a path to dApp development that can actually be applied generally. And this is the paradox of specificity. And so I'm going to kind of show you some things here, but essentially the paradox of specificity is, you know, we spend a lot of time making things very narrow and specific to our needs. And then it's usually much easier to adapt something that has been purpose-built and serves one need well into something that generalizes to serve a whole bunch of needs. We're setting out to make something generalized usually ends up less than ideal. And so now that things are starting to mature, we're feeling better about the state of it. We just had to set ourselves up for success. And I think this could change the ecosystem in a very positive way. I'm glad that you like my quote here. It's supposed to be a play on my experimental kind of archaeology from before. So yeah, this is how I feel about abstraction in general, though. Like it's almost like how we like to say things in math are discovered, right? Instead of trying to create the abstraction, it should be from looking at the state of your code base, what things are related to each other, what types kind of play nicely together, and building on that, like strengthening that association versus just saying like, I'm going to have an interface here that does this and that and whatever. Like it's better to discover it through the actual use of your code. It's more like, what would you call it? Compression oriented programming. You're acting like a text compressor or something. You're just pulling out the commonalities. I tend to like that. And so what we end up with is something where there's kind of just one main source, one main library, very small, very tight. Kind of the tooling is all very integrated. It's doing the transaction building, flat encoding, seaborn encoding, on-chain and off-chain code. It's very clear and structured, and it's very performant, and it's correct, and there's a lot of security guarantees baked in. Now, there's going to be a lot of verification that needs to be done there, and we're aware of that, and that's also part of the reason why we're reaching out to the foundation, right, to get more eyes on it, to get more critique, to get more insight, and see what it would take to bring this to everyone else, and also in a form that is preferable or agreeable to the people who are potentially going to be using it. So we have kind of compiled a whole lot of information that, again, was out there, but the discoverability was low, and we want to up the discoverability. We want to contribute back to the community. And so what I want to do now, just before I guess I can close this off before I give a little demo here, but yeah, I care about developer experience. I think that developer experience is, we optimize for, how long it takes a program to run, and how long it takes in memory, CPU, whatever. We don't optimize for like the developer, right? Running a Nix build and then waiting, and going and getting lunch and then coming back, you're going to dump that whole context from your problem solving. You're just going to be, we want to prioritize very fast iterations and being able to quickly change things and see the outcome of those changes. It just becomes a lot more of an enjoyable experience. And so I guess let's show some, I guess before I go into the demo, does anyone have any questions? So yeah, so there's a couple of little things here. So one is like Cardano CLI needing an entire cheat sheet and flowchart is kind of insane to me. This was another kind of reason we wanted to go a different way. And let's just look at the icon model for a second here, the vesting contract, just as a comparison. So one of the reasons that we didn't go with Icon is I didn't like that it's mostly focused on the on-chain experience, even though to get things to run on-chain, you have to do a whole bunch of work off-chain, right? Transaction building and designing your product around it and that sort of thing. So let's look at a simple vesting contract in Icon. I hope this is like visible. This is just from the Icon official site. This is just like the official vesting contract, and it's a very simplified vesting contract. And so we've tried to essentially create the same thing. So we have these uses here. We have these imports that are, you know, taking certain types into bringing them into scope. We have our datum, and then we have this validator for vesting that has a spend. This takes a few arguments. And the actual like logic is fairly straightforward, right? We just have some datum and we grab it out and we hope that it's in the right shape. We check that either this is signed or that these two conditions are true. So we have this and here. And this syntax I find is kind of awkward as well, because it's like or, and then here's the two conditions, and then it's like and then here are the conditions. And even that is just like, it's a little strange. And so we have either it's signed by the beneficiary and it's valid after the lock range, or it's signed by the owner. And in either of those cases, we can spend that UTXO. And then they have some tests that they have, you know, you have to import all these testing libraries. You have to check all of these things. We have to create this fake datum and we have to unlock, right? And this is sort of fine. You do need to do this setup work. But what I don't like is that it is kind of separate from the integration of actually running it on chain. And then if we're gonna, so we kind of have to repeat ourselves, right? So this is kind of building the transaction in a way. And then you come down to the setup work here, this is actually writing the code for it to operate on chain. And there's a lot, right? And then you have this MGS code here, which effectively repeats the logic for the smart contract, right? And so there's a lot here. And if we go ahead and we run that, I just want to have that as a baseline. If we go ahead and we run that, we get a 128,000 memory and 52 million CPU. So that is what we're looking for the vesting contract, right? And so let's take a look at what it looks like to write a smart contract in, I guess we'll say APLC for now, but so thankfully you don't have to write this. You don't have to write the APLC. So if we look at the Icon vesting Jai file, this is the same smart contract effectively. And I will show the Icon vesting types, which is just the datum, right? So we have a similar kind of setup. We have this datum, which is just a regular struct. We have this, we have the smart contract here, and we are just taking this datum, parsing it out from whatever the datum was in the input. So we're going through all of the inputs, and we are grabbing out the datum if it exists, and then we're going to be checking either the same condition. So is the signature of the owner or is the signature of the beneficiary, and have we locked for the correct amount of time, right? Now, if we want to run something like this, I like to focus more on what will actually be happening to get this on chain. And let me move this to the side here. So, yes. And so when we have this, I have just a simple test Icon vesting thing. And this test Icon vesting is, it does a bunch more setup. So it's like we have this runtime here, and the runtime kind of represents the current state of whether you're running on a mock chain, pre-prod, mainnet, whatever you're doing. We have the ability to grab a validator. That validator will be added to transactions if necessary. We can figure out what the address is, and we can just print it out. We create our datum, and then we build the transaction we submit here. And this is what it takes to build a transaction. So we're just paying to somebody, and we call submit and wait. This is doing everything. So the transaction is, you know, CBOR encoded, the validators are flat encoded, all of that stuff's happening. We are doing coin selection, and then we are selecting from the wallet that you give us. And then, you know, that's kind of done. When it's done submitting, we're then going to figure out what that ref is so that we can spend it in the second transaction. And then we're submitting that. That's essentially what's going on. So this would be like an integration test, but it actually operates as like a regular test. So let's take a look at what that looks like. So let me see here. If I go to that same window where we ran the icon, what we can see is that I can run this test icon vesting, right? And this is running in a mock chain. So kind of like the PAB, but we've tried to make it actually not have differences between the chain, and if not, it's like it's really quick, right? And so you can see here, it did all of those things. It submitted, and then it estimated, and then it submitted, right? And so that's it, right? And so that's our success. And you'd say, okay, well, look, that's half the memory and a fifth of the CPU. And you might be saying, okay, well, sure, that's on a mock chain. Well, let's just like toggle it on chain really quickly. And let's just run it again. And so now we're submitting on pre-prod, the exact same code path, no changes, while running, at runtime. I didn't recompile. And now we're going to be submitting on pre-prod. And so this is just it's just waiting because we're calling submit and wait. And that was the first transaction that pays to the validator. And now this is the second one that does the script interaction. We have the CBOR here just as like a debug output. And yeah, we'll just wait for that. And there we go. And so these will show up on pre-prod, and I can show them off after. But that is our real vesting contract. And if we want to compile that vesting contract, it's very quick to do so. It's actually only, it's quicker than you'd even think, just because writing out and reading from the, like doing the printing is actually the bottleneck here, funny enough. And so, yeah, we can do a whole bunch of stuff. We can do, but that's kind of the general flow. So we have a smart contract, and that smart contract is just written in Jai. We can share code and types across the on-chain and off-chain code. And the same will be true when you do it in other languages, because it will just be, we can essentially change that front end. We get a lot of the lexing and parsing stuff for free, a lot of the type checking for free, and we can releases and binaries for all the different platforms. Any questions? Yes.
Do you hear me well? So from what I read, Jai comes from a gaming background.
It does, yes.
The language. So how do you deal with the things like you don't need to have numbers that have a limited size and things like that if you use the types of that language?
Are you saying like the Jai, because it's using like bite-sized types, so like U64, U32 versus like integers that grow or shrink in like Haskell?
Yeah, I suppose, yeah.
Yeah, so there's, I mean, there's always going to be a bound, right? So we don't need Haskell's, especially if we're dealing with Plutus, there's always going to be a bound, because it's like the bigger the number, the more things are going to cost in certain scenarios. So you should kind of always know what the min and max bound are for data that you're kind of working with. Like, it's never going to be, this number could be anything, right?
Yeah, there are numbers that can grow, like much more than U64.
Yeah, but we can use U256, we can use U512, like that is something that we could do, yeah. So there are big number types, just like there are in pretty much any language.
Okay, yeah, I mean, yeah, that's a question both for usability and also for security, because we have seen a lot of hacks that happened like a few months ago related to wrong handling of sizes of integers.
Yeah.
Especially there was one on Sui like 2 months ago, which was due to that, and like 300 million, something like that, hack.
Yeah, so for the on-chain and off-chain code, the off-chain code, it actually, it's not as important, because the on-chain code, when it becomes Plutus, the numbers in Plutus don't really have a bound. So the on-chain code, it can never actually be subject to this type of issue, because UPLC in general doesn't have this type of issue. You can't overflow or underflow in UPLC. So when we emit the code, so even if you're using like a U64 in your code, just because that's what you've done, when it's compiled, there is no size integer type in UPLC, so it just becomes the correct thing. And on the off-chain code, you just use the number that is for the right bound. So right now I have value U64. This is actually parameterized, and you will get underflow and overflow checks automatically, which you have to actually explicitly turn off. So if I make this a smaller number and things start underflowing or over underflowing, that will really only affect the integration code, which means it will never actually affect the on-chain code. So that's totally secure there.
Okay, thanks.
Or no, please.
Yeah, I was curious. How do you about the whole off-chain on-chain integration? How does this work for larger dApps? How do you? So, I guess my question is, how much of Jai are you using on off-chain? And are you building the whole application or the whole system using Jai? Are you interfacing with other stuff? How does that work?
Currently, everything is done in Jai.
Okay.
Off-chain, on-chain, application code, Windows, views, web servers, AWS deployments, everything. So just keeping it all together, keeping it in a nice fast place, because now it's like if I need to change something or whatever, redeploy, we're talking about minutes, not days, or like seconds, not hours. Like it is a huge boon. And it's not really the language per se that is the cause of that. It's just like not having the friction and the accidental complexity. So this could be translated to other spaces, other ecosystems. We can even just like cross compile to, or I should say transpile to different languages if we need to. But yeah, currently everything is done in Jai, and that is just kind of been a boon for productivity and acceleration. Yeah.
Yeah, I'm just asking because I'm unfortunately old enough to having been there when there was when GWT was all rage.
Yeah.
And on face value, it sounded like a great idea. Like you do, one language to rule them all, and you do everything in Java, and it's supposed to be fast and transparent and interoperable and whatnot. Like I like to say, in theory, there is no difference between practice and theory, but in practice there is. So in this case, my general experience with mixing up languages and in very different execution environments is not great. But I'm willing to be. I mean, I'm happy to change my mind. But
Sure. Yeah. And I think that's a great thing to bring up, because that is so generally true. Like I get exactly what you're saying. And Jai just kind of, one of the big language features around Jai is that there's no magic. And what I mean by that is that like, it essentially just gives you access to, in this case, like the hardware, right? So like the point of it is not to make things easy for you. The point of it is to provide a sane interface to what exists. And what it treats its libraries and its first, like as a compiler, what it's doing is there's no build tool outside the compiler. There is no package management. There is no caching. There is no, like, everything is declared in the file. So if you're going to write like a meta program, the meta program is in Jai. It's all in there. And there's no magic in that. It's not trying to hide things from you. So like if you're using Icon, it's trying to, in a way, it's trying to enforce its own flavor of UPLC on you by hiding things behind, libraries, packages, whatever. What we've done is we followed the methodology of just exposing things as they are. So you'll notice that, for example, in the validator on the right pane there, you'll see that it just takes a script context, right? Which is exactly what the signature of a Plutus V3 smart contract is. It is just script context to effectively unit, right? And we don't impose any structure aside from what actually exists in the specification. So if your validator takes, a script context, anything you want to do that script context, you can do in here. And the structures you use are just like simple, and they map one-to-one in the way that you would expect. And so that is like a property of Jai that we've also just carried forward into our development process and our practice when building this out, because yeah, that kind of that magic kind of like hinders you at a certain point. At a certain point, you want to make sane decisions about what you're doing, or you want to have control over performance or what's actually happening, right? We want to make sure that what's actually happening is always like paramount. And I find the issue that people, when they try to unify things using one language, do is they try and create an API that is almost too simple. And then they kind of fail the API design, which is like, you probably want different levels of functionality based on where you're at. So when you're first starting a project, you want like simple, stupid things. You want to just be able to, build transaction and then submit, right? But then there's going to be later on down the road, you need that API to adapt with you, where suddenly it's like, well, now I really care about if this is on-chain or off-chain, or like what the actual fee is and how I'm computing the script fee, whatever. Like you need to have those points to be able to change that. And I think a lot of not having OOP practices and things like that is really nice. Like you just have a struct with data, right? You just take your information, you can look at it, you can see how it's represented, and you can make changes to it. And you can choose to do with that what you will, and it results in being a little more flexible. Does that make sense?
Yeah, I mean, I guess the proof is in the pudding. So I mean, these kind of things tend to be very much experiential.
Yeah.
And yeah, this leads, maybe I have another question, is how many giant developers there are out there?
How many giant developers, like total?
No, I mean, you get the idea, right? I mean, it seems like it's a very niche language. Okay,
Yeah.
Aiken is niche, but you only write smart contracts with Aiken.
Mhm.
The off-chain is written in JavaScript. So I was curious, like, yeah, what's the pool of developers,
So you're asking, are you asking in total or like BiFi?
imagining that we want to promote the use of Jai as a language for building dApps, how far can we reach, or what would be the outreach of such an effort?
I think like Jai is very, very, if you've used any imperative language at all, if you use JavaScript, if you use Python, if you use whatever, like Jai it's not really doing anything too crazy, right? You have declarations, you have, ifs, you have all of those sorts of things. It's just very straightforward. There's some like nicety for loops, things like that. But like, you don't necessarily need to, we're not necessarily going to be promoting Jai per se. Like our tooling's made in Jai, and we would make it available in Jai, but we can also make it like a library that, has bindings, or we can make it, a different front end for that sort of thing. So it's like, maybe you don't want to buy in to the kind of the benefits that we've seen from using it. But you don't really have to either. Like it'll be an option there. It is what we're going to continue to use. But at the same time, we are planning to have different front ends to this that are, let's say JavaScript or Python or whatever makes sense, because it would be fairly easy to do so. So yeah.
Skylar, Arno, did that answer your question, Arno, before we move on?
Sort of, yeah.
Okay, thank you. Skylar, we do have several other questions. Matteo, I will give you the opportunity to ask your question, but before that, I see there is a comment from Matthias Quest in the chat. He says here, Aiken always provides both options. For example, you can use the else handler in Validator if you're looking for low-level script context manipulation. Most people do prefer the high-level handlers, though, because it maps better to the mental model.
Yeah. So I can speak to that. Essentially, it's not just necessarily in like the script context. So this was like a very simple example, but it's just like even the things that are exposed in terms of manipulating lists and maps and things like that, and the control we have over built-ins and whatnot in Aiken. It's there's a lot there. I could probably write a series of articles about the things that I'm not necessarily a fan of, but of course you're right. Like you can go and do some of the low level, like you said, just having the right signature and doing the conditional on like what kind of the purpose you have. But I think the exposing of that directly is really important, because it's not like we want to have the script context there on like full view and be like, here's what you're actually working with, here's what it is. Even if someone isn't going to take the time to like learn that information and utilize it, it's like there and it's presented in its most raw, real form from the get-go. And we can have convenience on top of that, but it kind of aids back to that discoverability, right? Like if I go to the Aiken site and I'm looking for, information on how to do that, right? How obvious is it there? And like where, like it's just kind of a bigger thing. It's about that absence of discoverability. It's like, part of making it discoverable is making it discoverable directly in the code. I want it to be something someone can just kind of hack around on and figure out as they go, instead of having to intuit that there might be more to it or something else, right? Because if you provide an interface to somebody and it works in like the simple case, they're going to be immediately stuck when it doesn't work in the simple case, and they're not going to necessarily know how to go from there. And if we can guide them with like error messages or types or things like that, like it's going to aid in that discoverability in a huge way.
Thank you, Skylar. Matteo, I will come to you just in a bit. Skylar, do you want to move on to, because we have, let's say, 5 minutes left, and you've shown the vesting contract example. Do you want to show the example with the APLC where, let's say, it's visible how let's say the cost for
Oh yeah, let me talk a bit about the costs just to kind of make that more concrete. So we had the vesting contract that I showed in Icon, and we had the vesting contract that I showed in Jai. And what you saw with the vesting contract in Jai is the on-chain execution cost was about half the memory and a fifth of the CPU. That fifth of CPU, or like, or not a fifth of the CPU. The reason it was so much lower, I have optimizations off. We haven't done anything crazy. We've just directly translated the Jai to UPLC, but we have that unrolling, right? We're not even like eta reducing, beta reducing, doing any of those things. I have all of that off. And the reason it's so much cheaper is explicitly because of what I talked about. I mean, I would have to see that. I'm running the exact one from the script.
So what you're measuring is not just the execution of the contract, it's also the construction of the transaction in Aiken, which obviously is going to be expensive because that's not meant for that.
So the construction of the transaction,
the construction of transaction right now,
CPU and mem on chain?
Yes, because of the way the test is written. So what the test shows you is that it's the cost of constructing the transaction and running the validator. If you pull the transaction out of the test, put it in a constant so that it gets evaluated at compile time, then you can actually measure the cost of running your validator. And the actual cost is, well, 18K CPU memory and 5.4 million CPU.
Okay. I mean, we could still go much, much lower than that. But at the same time, yeah, I would love to go through that. If you can send me a resource on that or just some confirmation of that, like I would love to do the test again, and then I can get out some much better numbers, and then we can go from there. But yeah, that's interesting that it's measuring things that aren't. So is it just because it's all written in Icon? Is that why that it's like when it's executing, it's considering because you've written that code in Icon, it's considering that all in CPU and memory?
Yeah, of course. So
okay.
It's going to consider everything that is written in your test, right? The test is very much just a big UPLC program.
Okay.
The only thing Aiken does is measuring the execution of that program, which includes your test fixtures.
Okay. Yeah, that makes sense. So we'll evaluate how we demo that then, and I will make sure that it's a more fair comparison in that case.
Let's hear.
Yeah.
So I really like a lot of things that you presented. One thing I'm maybe lacking is better understanding what you are looking for, feedback, because we can like argue and like nerd about things all day on details and less details. But yeah, I was missing maybe a little bit what you are waiting for exactly.
Sure. Yeah.
Presentation. And also just another question is IOHK is I have a few initiatives right now about formal verifications of the contracts written mainly. They are starting with UPLC and going to Plinth and then maybe Aiken. How hard do you think the syntax of this language makes it to prevent the things you will need for statistical analysis of those kind of problems?
I would say that if they're starting with UPLC, then I think we can just go and reason from the UPLC, really. If they're starting with UPLC and we're targeting UPLC, a lot of that formal verification, if we're going to define what we say the contract is able to do and formally verify it, I think that can be done just right from, the compiled output. So unless I'm missing something, I think that would be good. Though it would be nice to also have a layer on top of the higher level language for some same guarantees there. So I don't think it would be that difficult per se. I know state might add some difficulty as compared to something that's like a Lambda language where it's just kind of one big expression. But I feel like there's been a lot of progress made in that field where I don't see it as much of a problem, but I could be wrong.
Thanks.
Thank you. Yeah, Skylar, please continue. We have, by the way, officially 1 minute left, but I'm happy to give you an extra minute just to wrap that up.
Sure. Yeah. And as far as like kind of what we're looking for, it's really just to start to get eyes on this, because again, we've made something that's specific for us, but having it kind of all integrated and having it all here and kind of avoiding a lot of that accidental complexity, I feel like it is, it's kind of a dream in terms of developer experience. And I think that we could adopt that and give it to the greater community and make it something that's more in line to build with. Though again, it doesn't have to be with Jai explicitly. The Jai can essentially be the back end, and other languages can become the front end. But having kind of like a one-stop shop to set up and build, right? I think would be a big deal. Yeah. And then also the information gained and the documentation that we plan to release that just kind of starts to tackle that problem of discoverability.
Thank you so much, Skylar, for this presentation, for joining us here today, of course, and presenting what we're calling now the dApp PLC. It has been very informative, and I love the fact that you earlier mentioned the word developer experience. This is something that definitely has been a hot topic in previous weeks, and I do think, let's say, having the community build certain tools like this, does contribute to this. And I do want to thank you for the presentation today, Skylar.
Yeah, thank you for having me, and thanks for hearing me out. And I love the conversation. I think it's important that we all stay honest in this sort of work, and there's always improvements that can be made. And so yeah, it's much appreciated. Thank you.